Now, there's a simple experiment that I like to do in class in order to demonstrate the qualitative importance of anisotropy, namely the possible normal shear, or for that matter, shear normal coupling. Remember that it's not something that necessarily arises. For instance, we've seen that in the specific orthotropy case that we discussed in class, we did not have normal shear coupling because of the orientation of the fibers, which aligned with, in some sense, the coordinate or ultimately the loading directions in a sense. And but in general, we could have it. So now, this is an example that I like. Even in class, it looks like sort of a hand trick, but it's not. So because I like it, I'm going to also record it and see if you can get something out of it. So what will follow is actually a numerical example that is perhaps slightly more convincing and more demonstrative. All right, so what I have is a simple sheet of paper. It turns out paper, because of the random orientation of the fibers of paper fibers inside its cellulose fibers, whatever, it's an isotropic material with respect to in-plane behavior. And therefore, it is not expected to display a normal shear coupling. So if I try to bend this right sheet, so bending moment induces normal stresses, and as a result of that, I expect only normal strains to form. In other words, I do not expect some out of plane deformation when I bend the plate like this, when I bend this paper sheet like this. An out of plane deformation would indicate some type of shear. So for instance, this type of motion would be shear. So all I'm trying to do is bend it, and if the material is free to move with respect to shear, and if it wants to, that would indicate normal shear coupling. I'm only putting normal stresses or normal motion, and as a result of that, I expect only normal motion, a normal mode, and no shear mode because it's an isotropic material. So to check that, I'm going to let the material be free to move along the out of plane direction, so that would be towards the screen in this case, and I'm going to do that by letting this paper rest on my fingertips, and I'm going to hold it as lightly as possible so that I am not applying any tangential force with respect to the plane of the plate, so that if the paper, or I keep saying plate, if you like, it's a plate, so that if it wants to move towards you or away from you, then it will be able to do so. So then I try to bend it without any constraints along the remaining two directions with respect to out of plane behavior, and well, it doesn't move in that direction because this is an isotropic material. If I try to bend it, normal stresses alone, a bending moment, I expect only a normal mode of deformation, which is bending. Okay, so that is isotropic. No surprise, right? So here is where the part that sort of is maybe not too convincing comes in, but I like it. So what I've done is I've taken that paper, and on it I have put cardboard along a preferred direction, not along the axis of the paper, which would be the major axis when I load it, okay? Because in that case, it turns out you don't observe normal shear coupling. The bending is very much like the isotropic paper that I gave you, because those normal shear coupling terms are zero. But it turns out if you orient it at another angle, and if my loading is still with respect to the original axis is that, if you like, that's like X, if you like, and the fibers are not running along the X direction, so now what's going to happen is we will get normal shear coupling. So in other words, if you like, the compliance matrix that gives the solution to this problem, it will have off-diagonal terms. What that means is that when I try to put a normal mode of deformation as a consequence of that loading, I will get deformation that is out of plane, that has to do with shear. So that will indicate that the paper will do something strange. Now I'm going to hold it as lightly as possible again, and I'm just going to try to bend it, okay? So I'm not constraining motion that is into or away from the screen. So now I try to just bend it as lightly as possible without any constraint. And as I do that, the paper tries to slip out of my hands. Let me do that again. So I load it very slightly, and the paper tries to rotate. And you see what's trying to happen is that the fibers are trying to get oriented towards you, away from the bending moment, away from the direction of moment. So it's trying to rotate towards the direction of least resistance, which is the out of plane, towards the screen or out of the screen, right? So that was a behavior that we did not observe with the paper, without any strengthening, if you like, without any fibers. But when I had fibers running like this, that's what we observe, rotation in this direction, right? So if the fibers were running along the other direction, I would probably observe rotation in the other direction, right? But presently, that's the way they're oriented, and as I try to impose simple bending moment on it, the paper tries to rotate, which is an unusual behavior. Unusual in the sense that our expectations are always based on isotropy, while this material is not isotropic, and hence you get this normal shear coupling out of it.